So now we're kind of looking at some more tests. So section 10.4 puts together these tests, the divergence and integral tests. So a couple things we need to talk about here when it talks to convergence. Let's say you have a series, and let's say this series converges. So add up a1 plus a2 plus a3, blah, blah, blah. Let's say then this adds up to a finite number. Let's say that adds up to L. You follow? Now, what if I just ignore the first 99 terms? Is that gonna affect whether or not this new series converges or not? I mean, it'll still add up to something. It's not going to add up to L though. Well, it may not add up to L because you're ignoring the first 99 terms. You follow? But this will still converge. Does that make sense or not? And likewise, if this thing diverged, if the original diverged, does it matter if we leave off the first 99 terms? Because at the end of the day, what determines convergence or divergence is a limit as n goes off to what? Infinity of the partial sums. You follow? So whether so let's say you had the first billion terms. Even though that's a lot, if you add up a billion terms, they're going to add up to what kind of number? A finite number. So if the limit ends up being a finite number, then you just add that finite number to it. You with me? That doesn't affect if it went to a number or not. If your limit blows up to infinity, and here's a finite number, is that going to affect it blowing up to infinity? No. If you have a limit that does this and oscillates around and can't settle down between like -5 and 5, if you add a finite number to that, that's just going to make it bounce around that finite number plus or minus what? 5. You with me or not? So one of the big things you have to get through, and we kind of talked about it last week when we looked at improper integrals. Where you start, a finite number of terms. A finite number of terms is not going to impact whether or not something converges or not. So that's the thing here that's in bold. So one of the, once again, a lot of what you're going to do in this chapter and the next chapter, I mean, you can mindlessly grind problems, but what you're going to really have to do is just kind of sit down and just think about this stuff and try to make sense of it, because you're wrestling with these notions of infinity. So a lot of times what you'll see is you'll just, I won't tell you, like when we do some theorems and stuff, I'll just have K down there and you can start it at whatever. Now, once again, we can always re-index everything. We can re-index everything to start at whatever K value you want. You could always have things start at K equals 1, you just redo the sequence or whatever, but in general, it's what's going on as you go off to infinity. So let's talk about our first test today, the divergence test. Now, first off, if you look at the name, it's called the divergence test, which means this test is only used to show if a series does what? Diverges. If you find yourself thinking or writing down the series converges by the divergence test, that should tell you, okay? And that tends to happen because number one, it's summertime, so everything's coming twice as fast. And number two, you have to be very careful with the logic here. So here's kind of the buildup. Suppose we have a series that does in fact converge. Suppose AK converges. All right. then that means that the limit as n goes to infinity of the nth partial sum goes to some number L. That's a real number. So we talked about this, I don't know if it was yesterday or the day before. If the limit as n goes to infinity of s sub n is L, what's the limit as n goes to infinity of s sub n minus 1? So remember, we're just looking at S1, S2, S3. Where are those S's going? It's going to the same place. It's also going to L. You follow or not? It's just one step behind the other one. Okay? We also talked about this yesterday, that to get to Sn, and we actually use this today, to get the Sn, you just take Sn minus 1 and tack on the An. So the sum of the first n terms is the sum of the first n minus 1 terms plus the nth terms. We talked about that yesterday, which means that a sub n could be written this way. So we talked about this, was it yesterday or the day before? I think probably yesterday. So let's take the limit as n goes off to infinity of a sub n. You know that Sn goes to L. S sub n goes to L. So this goes to L minus L, which is what? 0. Make sense or not? So what this says is, if you have a series converges, then the limit of the individual terms has to go to 0. And hopefully that just kind of makes quote unquote number sense. Because if you're adding up infinitely many things, and those things are going to like 2, then it'd be like you're adding up infinitely many 2's eventually. You follow? And that's just going to blow up. The only chance you have to have an infinite number of things add up to something is for those individual things to go to 0. Does that make sense or not? Okay. So once again, this is a conditional statement. We've got an if part, and then we have a then part. So this is called a conditional. So let me ask you this. If the limit as k goes to infinity of a sub k is not 0, then what can you say, if anything? Is it possible for the series to converge? No, because if it did converge, I'm guaranteed that the limit goes to what? So therefore, we can conclude that the series diverges. And this is the divergence test. If the limit of the individual terms doesn't go to 0, then the series can't possibly converge. It must diverge. So here's how I like to write it, though. If the limit as k goes to infinity of a sub k is not 0, then the series a sub k, it doesn't matter where k starts, diverges. And then I have a little corollary. If the limit as k goes to infinity of a sub k does equal 0, then we don't know what goes on with the series. It may converge, it may diverge. Do you see the difference in the logic there? Once again, I drive a gray car. If you see me driving a car, it will be what color? Gray. If you see a gray car driving around, doesn't necessarily mean I'm in there. Maybe I'm in there, maybe I'm not. You follow? This is the same logic. If the limit doesn't go to 0, then it diverges. If the limit does go to 0, the test doesn't work. You just got to do something else. The test is inconclusive. Okay? You don't know anything. Maybe it works, maybe it doesn't. So once again, if your limit goes to 0 and you say, oh, if you start to write down series converges, but then you realize it converges by the divergence test, you know something isn't right. Follow? So here's, once again, okay. So we can use this to test whether or not series diverge. Or we should say we can test if they diverge. So let's take a look at the first one there. K goes from 2 to infinity of 2k over k minus 1. When I apply tests, the divergence test is typically the first one I think about because it's usually the easiest to apply. Can I easily figure out what the limit is as k goes to infinity of this one? Yeah, what's that going to be? That's just going to be 2. Okay? So that means as k runs off, yeah. What's that?
You don't get shut this, or I didn't want to interrupt you.
Oh, no, that's fine.
We got my cadets out here. I didn't want them to interrupt you guys.
Oh, okay. No, we're good. We're playing with infinity, though, so it's a little volatile. All right? But yeah, you can shut the door.
Sure? Okay.
Yeah, it's totally fine.
Thank you.
Yep.
Thank you.
I'm just glad there's a window there. I don't like shut doors with no windows. That's how I knew, like, my new dean, she's great. If I go in there, she shuts the door. I'm like, what are you shutting the door for? That's always a bad thing. No, I just don't, Basically, this says as k runs off to infinity, you're eventually adding up things that are going to look like 2. And what happens when you add up a bunch of 2s? It's going to go to what? Infinity. So we can say, well, you know what? That ain't 0. So the series diverges by the what? Divergence test. It's literally in the name. You follow? And that's what you're going to have to do here is you're going to have to be writing up like these little mini proofs. You got to write little stories. Right? You could flip a coin, diverge, converge. The answer literally means nothing. It's like those trig identities. Remember when you did trig identities? All right, be like, here's a trig identity to verify. You had the answer literally right in front of you. You knew that the whole thing had to work out the tangent of 2 theta somehow. The meat was trying to figure out how to put all the pieces together. That's exactly what's happening here. All right, sum k goes from 0 to infinity, 1 over k factorial. Now before you freak out, what's 0 factorial again? 1. So this is actually totally cool at 0. Take the limit as k goes off to infinity of 1 over k factorial. What's going on with that? The numerator is always what? The denominator is k factorial, so that's getting bigger and bigger and bigger. So this limit is going to 0. So we don't know anything. Maybe it converges, maybe it diverges. Divergence test fails. In chapter 11, we'll actually prove this converges to E, of all things. But we don't know, there's no way we could know that based on what we know now. Let's take a look at number 3. K goes off to infinity. What happens to 1 over k? Goes to 0. So what's that tell us? Nothing. We don't know. So when the divergence test works, it's quick and it's in the name. The limit's not 0. If the limit of the terms isn't 0, series diverges. Take a look at number 4. Limit as k runs off to infinity of cosine of 3k. What happens to this limit? Yeah, it doesn't exist. It just kind of bounces around, right? This limit does not exist, which means it doesn't equal what? 0. So by the divergence test, the series diverges. You follow or not, folks? Because if that series would converge, the limit of the terms would have to go to 0, and it doesn't. Okay, so that's a divergence test. All right, let's take a closer look at this series. And I want to do enough here with the pictures here to kind of motivate the integral test, and then we'll stop, and then we'll finish up integral test and all the other good stuff tomorrow. Because I want to show you what's going on here, so you have a little bit of time to let it percolate in. But this series 1 over k, this is a famous series. It's called the harmonic series. And you think harmonic, you think, does it have something to do with music? And the answer is yes. So there's your Wikipedia moment today. What's the harmonic series have to do with harmonics? Now, it's not geometric because the k isn't in the exponent. It's not a telescoping series because there's no partial fractioning this. You follow? It's literally just one fraction. And the divergence test, we just tried the divergence test on it. Divergence test is worthless on this. Okay. However, remember yesterday we talked about how you can view these things as discrete integrals? So let's draw a picture. Okay. And I'm going to plot this. So I can think of the harmonic series as 1 plus a half plus a third plus a fourth plus blah blah blah. And so I can think of this as 1 times 1 plus a half times 1 plus a third times 1 plus blah blah blah. And so what I can do is I can think of this sum as adding up the area of these rectangles. So the area here is 1 square units. The area here would be, once again, it's 1 wide. So each of these has the width of 1. They're 1 wide. I forgot to put that in there. And then they're 1 over k tall. So this would be a half unit squared, a third unit squared. Okay. So if I connect these, this would be the function 1 over x. All right, and that's how I'm getting the height in each of those things. Is everyone cool with that? This is what we talked about yesterday. Now here's the thing though. Don't I know how to calculate the area under that curve? The green area I could calculate using a what? Using an integral. The integral starts where? And goes to where? Good golly, didn't we do that last week? We did this exact one last week. What happens to this? This goes to where? It blows up. Remember that? So let me ask you this. If the area under the green curve goes off to infinity, then what about the area of all these blocks? They're bigger than or equal to that, right? So they must also go to what? Infinity. So we can say, well, that's got to go to infinity. In other words, it's got to diverge, because whatever this is, we could argue that's bigger than or equal to this integral. And we know from last week that that integral diverges. Okay. So let's recall what we know about integrals like this. So recall, we did these last week. The integral from 1 to infinity, 1 over x to the p dx. They're going to diverge if p is less than or equal to 1, and they're going to converge if p is bigger than 1. And the reason is, if p is less than or equal to 1, when you go to integrate 1 over x to the p, you either get a natural log out if p is 1, or if p is less than 1, you end up with x's in the numerator of the antiderivative, which go off to infinity. If p is bigger than 1, then when you add 1 to that exponent, you're still going to be left with x's in the denominator, so the antiderivative then goes off to 0 when you do that. Okay, I know it seems like it's been a while, because it's been since last, when did we do these? It's been a week ago, right? Last Wednesday? Was it last Wednesday? I think it was last one. It was last Wednesday. So it's been a week, but it feels like 2 weeks because it's summertime. You follow? So we got to keep that in mind. Okay, these are going to be handy. And once again, does it matter really where we start here? We could really start at any positive number a. That's still going to happen because it's the limit as you go to infinity. All right, now let's switch gears. And let's look at this example. This kind of reminds you of what integral? Now we know this integral does what? Since that power is bigger than 1, we know this integral is going to converge. And the question is, can I do some kind of argument here to show that I can use this integral to make this work? Well, we have to modify things a little bit, because if we do the same argument we did and make the blocks the same way as we did before, we would have this happening. And does this tell us anything? I know that this is a finite number. You follow? This series would be bigger than a finite number. So could it still possibly blow up to infinity? Yeah. You see how that doesn't work for us here? So here's what we got to do. Is we got to try a different approach. Let's look at the limit. Let's do this. Let's look at this one. And here's what we'll do instead. We'll just start here. And instead of doing a left endpoint sum, we'll do a right endpoint sum. You follow or not, folks? So the sum from k goes from 2 to infinity. This would be less than or equal to the integral from 1 to infinity, 1 over x squared dx. We know from last week that this is a finite number. You with me or not? So I'm adding up all these things. I'm looking at their partial sums. The partial sums would represent the sum of these rectangles. You follow? Each additional rectangle, I get slightly more area. So the partial sums are an increasing sequence. You follow? And they're bounded above by whatever that finite number is. And so we have an increasing sequence bounded above. So by the completeness of the real numbers, which we talked about last Monday, we actually get that this actually does converge. You follow? And since the only difference between starting at k equal 2 is the first term, if this adds up to a finite number, then when we add on that first term, it will also add up to a finite number. Okay? So this is where I want to stop today, because I want you to think about this. I want you to think about these two arguments. All right? The argument that this series diverges, and the argument about why this series converges. And once again, the arguments, well, we kind of talked through them, but they're also written down. So you want to go back and study those to see what's actually going on. Because here's the thing, right? What's nice about these two, and these two, these are quite the pair. These are quite the pair. Right? The divergence test, both of these things have, their terms go to 0, both of them. You follow? But just like last week, when we were integrating, both of those functions went to 0. But the function 1 over x didn't get to 0 fast enough for that area to converge to a finite number, but the 1 over x squared did. The same thing's happening here at the level of sequences. So take some time, draw some pictures, work through that argument. We can use improper, in certain cases, in other words, as long as the picture looks like the pictures we drew today, we can use improper integrals from last week to help us figure out whether or not these types of infinite series converge or not. Now, we don't know if they converge. We don't know what they converge to. They converge to some finite number, and we can get an upper bound of that finite number using the integrals. That's what we'll talk about next time, the remainder theorem. But we're trying to tie together what we did before with what we're doing now. Okay? We're really looking at these sums as being, these infinite series as being discrete versions of the integrals we know and love from before. So that's kind of where we're going to pick up today. We showed that this series diverged yesterday. We showed that this series yesterday converged. And the way we did it is we compared them to these improper integrals that we knew about. Okay? So something you want to keep in mind that's going to be helpful today is if you have integral 1 over x to the p, and we're going to assume that a is positive here, so we're not worrying about the vertical asymptote. We're just looking at the end behavior here. This thing converges if p is bigger than 1, and it diverges otherwise. So if p is less than or equal to 1. We talked about those kinds of things last week. But the argument we used to connect these two integrals with these two series forms the foundation of another test to check to see whether or not a series converges. So let's take a look at these pictures again. And so in this picture, remember we can look at the area of these rectangles representing the sum of the series. And the area then beneath the curve is going to be less than or equal to the sum of the series. Or if we shift the index, we can get the sum of the series this way, and then the area of the curve would be bigger than the sum of the series. Right? So if we know, for example, the integral diverges, then the area under the curve would be always less than the area determined by the sequence. So if the area blows up to infinity, then that would force the series to blow up to infinity. On the other hand, if the series added up to a finite number, then the area would also have to add up to a finite number. You follow? Because it would be smaller. This picture, if the area adds up to a finite number, then the series would have to add up to a finite number. If the series blew up to infinity, the area would have to blow up to infinity. You follow or not, folks? Okay? So this is the basis for what's called the integral test. So in order to use the integral test, you need three conditions on your function. You need your function to be continuous to make sure that the integral is going to be defined. You need it to be positive and decreasing on some interval. Then it turns out that the integral and the series are sort of tied together. Their fates are the same. They either both converge or they both diverge. And the reasoning is that geometric notion that we talked about yesterday, that we kind of talked again about just a couple seconds ago. Okay? So you see how these pictures kind of give you that argument? Remember, those blocks represent the sum of the series, and then you've got the area under the curve. Now, if the case that they do converge, if that's the case you're in, that they both converge, then many times we can find the actual retail value of the integral. And if that adds up to like 2, and we're comparing it with the series, then that series doesn't necessarily have to add up to 2. So the improper integral and the series both converge. So if that's the case you're in, they don't need to converge to the same number. But what we can do, and we'll see in a little bit what we can do, is we can use the value of the integral to help us approximate the value of the series. So example 2 here, which is a video, takes each of these series and it looks at the corresponding integrals. And it goes through the conditions of the integral test. So let's just write down what integrals you'd be comparing these to. So basically you take the sum, k goes from 1 to infinity, 1 over the square root of k plus 3, and then you would smooth that out. The sum would be the integral. You'd go from 1 to infinity. And instead of the variable k, we're going to switch over to the continuous variable what? X. So there'd be 1 over square root x plus 3 dx. So the function here you'd be looking at is that. And you would have to check to make sure that the function is continuous, positive, and decreasing on the interval 1 to infinity. Then you'd have to go in and look at the integral itself. Does it converge or diverge? And that'll tell you about the original series. You follow? What would be the integral you'd be looking at here for number 2? Be the integral from where to where? 1 to infinity. And what would be the integrand? Yep. dx. You need, once again, here'd be your f of x. And you'd have to check all three conditions. And once again, these you do all this on the video, and then you figure out what's going on with that integral. And last but not least, what would be the integral we'd be looking at here? Start at 2 to infinity. And now what would be the function in there? And we'd have to check 3 conditions and see what happens to the integral. Okay? So these last two, the integrals converge and therefore the series converges. The first one, the integral diverges and therefore the series diverges. But the video has all the details on how you would go about writing something that up. You follow? But the integral test, once again, it's going to end up being like a test of last resort for us because you have to do a lot of things. You have to first verify that your function satisfies the conditions for the integral test, and then you still have to go through the improper integral, which is like what we did last week. You follow? But the thing that the integral test gives us that we are grateful for is the p-series test. So the p-series test, like geometric series, like the divergence test, is going to be one of those tests that's typically quick to apply, and when you can apply it, we know exactly what's going to happen. So here's the big theorem. P-series. Technically speaking, a p-series is a series of the form k goes from 1 to infinity, 1 over k to the p. And the integral test, and these are like the two we did yesterday, the integral test tells you that the fate of this p-series is exactly the same as the fate of these integrals, which the fate of these integrals we talked about last week, and we remind ourselves today. So p-series says if you have a series like this, if p is greater than 1, then the series converges. If p is less than or equal to 1, the series diverges. Easy peasy, okay? Now, let's take this to the next level. First off, does convergence really matter on the first finite number of terms? Okay, so we talked about this yesterday. Does convergence or divergence matter? Or does a finite number of terms, is that going to affect convergence or divergence? No. So you could really start this anywhere you want. That's going to be fine. Because what determines convergence and divergence is what is the behavior of this thing as you go off to infinity. So you can really start wherever you want. And what about this 1 here? Let's say let's say you got a non-zero number c. Does multiplying something by c, does that affect if it converges or diverges? If it adds up to a finite number and you multiply it by c, is that still a finite number? If it blows up to infinity and you multiply it by c, is that still going to go to infinity? Yeah. So we can actually write that. We can kind of fix that as well. So if you have any series that looks like this, it's essentially a p-series. Okay? And you can tell whether or not it converges just by looking at it and looking at that power p. So for example, take a look at this first series. K times the square root of k. That's really k to what power? 3/2. That's a p-series. What's the p? 3/2. What's important about it? It's bigger than what? 1. Series converges. We're done. You follow? P-series. P is bigger than 1. Converges. We're done. What's telling us that in the background is the integral test, but we don't have to go through the integral test. Because of the work we did with improper integrals last week, we get these things more or less for free. Let's take a look at number 2. Number 2, we're looking at k goes from 10 to infinity of the 4th root of k over k. So let's take a look at this. The 4th root of k is really k to what power? 1/4. And that's divided by k to the first power. So that's really 1 over k to the what? 3/4. Now, technically, is it a p-series? No, because we're starting at k equals what? 10. But does the value of those first 9 terms, if I add up those first 9 terms, is that going to change whether or not this adds up to a finite number or not? No. So I can go ahead and say, okay, this p-series, p is what here? 3/4. And what's important about the power p? Is it bigger than 1? Nope, it's what? Less than or equal to 1. So that tells me that the series is going to do what? Diverge. Okay. Even though those terms are going to go to 0, they don't go to 0 fast enough. When you add up all those terms, they're going to blow up to infinity. And the first 9 terms isn't going to affect that. You follow? They'll still blow up. Take a look at number 3. I got the sum, k goes from 1 to infinity, of 3 over k. Is that technically a p-series? No. But what do we know about this one? That's our friend, the what? This is a p-series. P is what here? What's the power? Is that less than or equal to 1? So this diverges. This is going to add up to infinity then. Right? It's a positive series, going to add up to infinity. This is just going to, I'm just multiplying by 3. So if this blows up, is this going to blow up? So this is essentially a p-series. So that's going to diverge as well. Make sense or not, folks? Okay. So if you're looking at all the tests we've learned so far, we've got the divergence test, which is pretty quick to apply. If the limit as k goes to infinity of a sub k is not 0, then the series diverges. That's usually pretty quick to see. We've got geometric series. If you've got a geometric series, this is going to converge only when the absolute value of the ratio is less than 1, and it'll diverge otherwise. Once again, we know exactly what happens. And geometric series are typically quick to spot because all the k's are in the exponents. And then we got p-series. And once again, it doesn't matter where it starts. P is bigger than 1, it's going to converge. P is less than or equal to 1, it's going to diverge. Okay. Now, off in the background, we do have the integral test. But once again, that's going to be a test that would be like a test of last resort, because we got to pull out the integral test, you got to pull everything out. It's a whole production, right? It's like a Thanksgiving dinner of a test, because you got to turn it into an integral. You got to check that the function satisfies the conditions, continuous, decreasing, positive. Then you have to go through the improper integral, which is like what we did last week. And then depending on that, what the result is, it's either going to converge or diverge. So the nice thing about the integral test, the p-series, and the geometric series is it tells you if it diverges or converges. You follow? The divergence test will only tell you if it does what? Diverges. It won't tell you about convergence or not. Right? So there you go. Now, what the integral test is good for is it helps us figure out remainders. Okay? So let's say you had a convergence series. So let's say you've got the sum, k goes from 1 to infinity, a sub k, A1, A2, A3 plus dot, dot, dot. And let's say this converges to some real number S. Unless it's a geometric series or unless it's a telescoping series, we're not going to, in general, we're not going to know what that number S is. You follow? So the best we can do is we can approximate it with partial sums. So here's what we're going to do. We're going to let S sub n be the nth partial sum, as it's always been. And we're going to let Rn be this. So basically, Rn is what's left over after the Sn. So Sn, you add up the first 1187 terms. Rn would be the rest. Okay? So oftentimes in the business, this is called the tail of the series. So the nth partial sum, we're adding up the first n terms of the series, and then the remainder, that's the tail, that's the rest of it. You follow? So for example, S1 would just be A1. R1 would be A2 plus A3 plus A4 plus everything else. You with me or not? It's called the remainder because it's the part of the series that's left over. S2 would be A1 plus A2. So R2 would start with what? You follow? S3 would be A1 plus A2 plus A3. R3 would start with who? A4 plus everything else. You follow? S11D7 would be the sum of the first 11D7 terms. Oops. So what would R11D7 start with? That would start with what? 118. So you see what the remainder is? So oftentimes when you hear remainder, you think, well, it's there's a division happening. That's not what's happening here. Remainder is literally the stuff that's left over. Right? It's the you just add up the first however many terms, and then the remainder is what's left over. So in the case of a convergent series is the nth partial sum plus the remainder. It's everything you get first n terms plus the rest. Oops. So this is the sum of the first n terms. And this is the rest. Bless you. So another way to think about the remainder is you can think of it as the error you get by approximating the actual retail value of the series by the nth partial sum. Does that make sense? So that would be the actual error. So for example, if I worked out Sn to be 3, and I worked out Rn to be 1, then my entire series would be 3 plus 1, which would be what? 4. You follow? So I can think of this as, if I approximated the S by the Sn, so I approximated S by 3, then the remainder, which is 1, would be the error. You follow? Now, if we knew exactly what the error was, we wouldn't have any error, would we? If I knew that Rn actually equaled 1, we wouldn't have an error anymore. You with me or not? So oftentimes what happens in this section and in what we're going to do next week is we'll have theorems that help us estimate the error. In other words, estimate the remainder. Okay? So when we talk about the remainder theorems in this course, we're not talking about remainders coming from divisions. We're talking about what's left over when we approximate the infinite series with their partial sums. These are going to help us estimate Rn in certain cases, which help us estimate the error incurred by approximating S, the actual retail value of the sum, by Sn. Okay? So that's what the remainder theorems are. And what's nice about the integral test is if we have all the pictures in the world that kind of tell us what the remainder theorem is for the integral test. So what's nice about the integral test is, you know, the function, and so therefore all the terms of the series have to be positive. So that means that the remainder is always going to be a positive number because it's just you're adding up terms. And so we can draw a picture to help us figure out an estimate for the remainder, which is what we'll do now. So suppose you've got a series, k equals 1 to infinity, a sub k, that converges by the integral test. Okay? So for example, any of those p series would be an example of a series that converges using the integral test. So we know that we're comparing this series to an integral where the function is positive, decreasing, and continuous. Which means the function is going to look more or less like the picture we had yesterday. Okay? So let's take a look here at, let's say you went up to n and you added up the first n terms. So then this would be n plus 1, n plus 2, on down the line. So my Rn would be then the sum of the tail, an plus 1 plus an plus 2, all the way down the line. And once again, we could draw a picture of that this way. So here's n plus 1, so the height of this would be a sub n plus 1. The width of this rectangle is 1, so that area would be an plus 1. That area would be an plus 2, and so on. You follow? So this would be less than or equal to the area under the curve starting at n. Do you see how the picture shows that, folks? And so that's the remainder theorem we have for the integral test. If you've got something that converges by the integral test, R sub n will be less than or equal to the improper integral n to infinity f of x dx. And that's the proof. Right? Moreover, what you can do then is if you look at the series, remember, the series is the nth partial sum plus the remainder. We know that the remainder is going to be less than or equal to the integral from n to infinity f of x dx. And now I can go back to this picture. And if I look at the integral from n plus 1 to infinity, let's do this. Now let's do the other picture. this integral. Integrate n plus 1 to infinity f of x dx. I can go in and do the other endpoint sum. I can make the endpoints do this. Right, so there's the an plus 1 there. An plus 2 there. And so this would be, whoops, let me write it over here. Right, so this would be less than or equal to the remainder. See how the geometry is helping us here or not, folks? So if you put these two pieces together, you've got Rn less or between the integral from m plus 1 to infinity f of x dx and the integral from n to infinity f of x dx. And now then if you just add the partial sum on through, that's the complete sum S, and you've got it between the nth partial sum and those two things. So you've got a bound then on what your sum actually is. We don't know exactly what it's going to be, but we can bound it using the remainder theorem, and then we can sandwich it using between those two values. So when you go back and review what we did the past couple days with the integral test, I really encourage you to draw those pictures we looked at, to see the relationship between the area of those blocks, how that ties in to the sum of the sequence, or to the series rather, which is the sum of the sequence, but ties into the series, and how that relates to the area under those curves. Because that's what's driving all of this, are these pictures. Okay? All right. All right, so this is a video, because once again we have to go through the improper integral. So you're going to show this series converges. We can do that together, because looking at this series, it's what kind of series? It's a P series. And what's P here? 3. And what's important about 3 for the P series? It's bigger than 1, so it's going to converge. All right. So I'm not going to, like I said, I'll leave it to the video to kind of work through the details here, do all the heavy lifting. But let's talk about S4 then. So S4, that's the fourth partial sum. That's the sum of the first 4 terms. So we'll go k equal 1 to 4, because the k starts at 1 here, 1 over k cubed. So that would be 1 over 1 cubed, plus 1 over 2 cubed, plus 1 over 3 cubed, plus 1 over 4 cubed. And you can use Desmos, and you'll get that number. You follow? The question is, how close is this number to the actual retail value of the entire infinite sub? That's when we're going to use the remainder. So the remainder theorem says that R sub 4 is going to be less than or equal to the integral from 4 to infinity of not 1 over k cubed, but 1 over x cubed dx. You follow? So then you're going to go off, and once again, we do all the details on the video to get what number this is. And this works out to be, I guess, 0.03125. And so that would be then the approximate error between what this is and then what the whole thing adds up to. You follow? So you can go through the video to see all the details of that, but that's kind of the gist of it.